All right, what about plant cells? Let's do the same thing again. We'll set up a beaker. We'll put salt water in there. So we'll say water potential is, real low, -9 or something. And it's in bars, but I'm not going to put the units just to save a little bit of space. I'll put my plant cell here, make it nice and fat so I can write in there. Plant cell has a solute potential of, I don't know, -4, let's say. I'm just making stuff up. But the pressure, you might say, oh, that's 1 or whatever. No, actually in a plant cell there's Turgor pressure. So we're going to say that's 3. I don't know. Maybe it's 3, maybe it's 2, 4, whatever. I'll just say 3. There's a certain amount of Turgor pressure, which keeps the plant cell strong. That's already in a normal, healthy plant cell. All right, the pressure out here is just atmospheric pressure, which is 1. So that's just from the air around us, and there's a certain amount of weight above us from the air and the atmosphere that's pushing down on us due to gravity. And that's what this is, 1 bar or 1 atmosphere. All right, so that's where we're at now. So let's take a look at the inside water potential, which is solute potential plus pressure potential. I'll just write it out once just to remind us. So that's going to be -4 plus 3 is -1. So water potential inside is -1, water potential outside -9, solute potential plus 1, pressure potential is -8 bars. All right. So which one is greater? We say -1 is greater than -8. This is smaller, so therefore water is going to diffuse from in to out. Water is going to diffuse out this way. All right, so then we draw it again after, just like we did before. And we take our plant cell, and we see this inside, shriveled up thing. And now it gets a little bit tricky, because now we're like, okay, what about the pressure in there, and what about, this and that? So let's just do the outside first. This is -9. This we know is going to be 1. That didn't change. Atmospheric pressure didn't change, and the cell is so small that our solution didn't change in any measurable way. So we said we waited, this is after, we waited long enough for everything for no more net movement. It's at equilibrium now. This is before, so this could be hours later or a day later or something like that. If there's no more net movement of water inside or out, that tells me that the solute has to be the same in here now. It's also going to be at -9. And the pressure is going to be at 1. And you might say, well, what about Turgor pressure? No, we lost all that Turgor pressure when the water diffused out. We no longer have that Turgor pressure. It's now, what we say that the cell is flaccid, which means it no longer has that strength and that support, and the plant would wilt in this situation. That's what salt does to plants. If you dump salt on your plants, they're going to wilt and die because all the water gets drawn out. But that's basically what we get to, is that our inside water potential is now going to be -8, and our outside water potential is also going to be still -8. So now they're equal. There's no more net movement of water inside or out of the plant cell. And I consider this the plant cell. This is just the empty cell wall that remains behind. This shriveled thing in the middle, that's the plant cell now. And that would cause it to die. All right, what about hypotonic? Let's check that out. This is a little bit more, I guess, normal for the plant, because plant cells are surrounded by, water, and usually a hypotonic state. So we said this was, what did I say, -4? Did I say negative? What did I say? Oh boy, I can't scroll now. Okay, well, I will just keep it -4. This was 1. We said out here it's going to be hypotonic, so pure water. So that's going to have a solute potential of, what did you say, 0? Very good. Pressure is 1. Okay, our inside is going to be -3. Our outside water potential is going to be 1. So which number is greater? Well, 1 is greater than -3. That's the higher number. So the water potential on the outside is greater than on the inside. Therefore, water is going to diffuse in from greater water potential to lesser water potential, it's going to make that swell a little bit. So let's check that out. Now what we're going to have is something quite interesting. So I'm going to make this really big. It's not supposed to be this big, but I want to have lots of space to write. All right, this is still the same. That's easy. This is still the same. That's still 1 atmospheric pressure. This is still pure water. So what happened now is this swelled up a little bit. Okay, so this maybe should be bulging a little bit here. Whatever. Okay. So now, if we had all that water diffusing in, the pressure is going to be, let's say, 3. Oh, you know something? This should have been 3 over here. I made a mistake. This should have been 3, so this would have been -1. -1. Still water diffuses in. Okay, that hasn't changed. All right, so let's say the pressure goes up to 3 in here. Well, if the pressure goes up to 3, then our, let's see, the outside is 1 still. If the pressure went up to 3, that tells me that my solute potential in here now has to be what? It has to be, okay, this is where it gets tricky. We said there's no more net movement of water inside or out afterwards if we waited long enough, which means our overall inside water potential has to be the same as the outside. It has to be 1. Well, in order to get this to be 1, if the pressure is 3, or actually the pressure is going to go up a little bit, so let's say it went up to 4, what does this have to be? If this went up to 4, this would have to be -3, because 4 plus -3 gives you an inside water potential of 1. So how do we explain that? Well, out here this stays the same, nothing's changed. This went up a little bit. This went from 3 to 4 because some of the water went in, increasing the pressure. So the pressure went up to 4. But what about this -3? Well, we said that in order to make this equal on both sides, no net movement anymore, the inside water potential has to be the same as the outside, so it has to be 1. In order to get that to be 1, if we have 4 plus what is 1? Well, 4 plus -3 makes 1, so that's -3. Okay, how do we logically explain that though? And the reason that happened is because it went from -4 to -3, it got more dilute because a bunch of water came in. That water came in, diluted the salt on the inside, and actually made the concentration on the inside a little bit more dilute, bringing that water potential to -3, having been -4. All right, well, I made a bunch of mistakes here, which probably made this way more confusing than it should have been, but at least I caught them at the end and I fixed them. Amira, I hope you don't see this.